Now, there is there are two more important aspects of convection. One is, okay, for both external convection and internal convection, we were imposing a velocity. There is a velocity that goes through the pipe. There is a velocity of the wind that goes around the body. That's the U infinity, or the UM. Now, what happens if we don't give any velocity? That's when we talk about stagnant air, for example. So this wall over there on my right? That wall, nobody's imposing any velocity on it. So you bet any money, there are flows of air there, because slight differences in temperature between the wall and the surroundings, right? So those flows now are interesting because you don't have an external velocity to impose, right? But they do have a velocity. So there is an additional challenge that is, here's a boundary layer, everything that you already know. But what velocity do I give to that boundary layer, right? That's the challenge here, and then new dimensionless groups are going to appear, right? And you're going to learn a lot about that. So this week is this external, natural convection that can be internal and external and internal, both. You're going to see that this week.
You used my time for introduction. Now we directly start our topic of this week, natural convection or free convection. It happens everywhere in our daily life. In a sealed light bulb, the fluid inside, the gas inside is still has some velocity. Some guy did a numerical simulation to see the motion of the air inside this light bulb. And in very cold winter days, we sometimes can see frosting on the inside surface of the window. But have you guys ever paid attention? Why does it always appear at the bottom of the window, not on the top? Keep this question in mind. We will work it out together. Also, our hand is not black magic, but that's the air get heated by our body temperature. Then it gets less denser and rise up. The same mechanism happens to the direction of sea breeze. At the daytime, the land has a higher temperature than that of the seawater. You see the air rises, and cools down by the water sinks above the seawater. It has a clockwise direction. But at night, because the seawater has a much larger specific heat, the water has a higher temperature than the land at night. So the air gets warmer on the side of the seawater, but cools down on the side of the land. It has the opposite direction of the breeze. Let's go through this chimney experiment together to see how natural convection works in still water.
In fact, I'm going to put a lot of food color. Oh, there we go.
right. The video shows how natural convection current works in the still water. We will in this week we will go through the physical mechanisms associated with the natural convection, which is a buoyancy-driven flow. And we will start from it very similar as external flow and internal flow. It can be laminar and can be turbulent as well. We will start from the most simple case, laminar flow on a vertical isothermal plate. Then investigate the effect of turbulence and go through all the empirical correlations to calculate the exact convection coefficient for different geometries. And when free convection and forced convection are at the same order of magnitude, how can we deal with it? Let's start with this simple case first to see what are the key factors to ensure the existence of natural convection. For the configuration on the left, we have two parallel horizontal plates. If I hit the bottom plate to set it as a higher temperature than the top plate, which means we have the bottom temperature larger than that of the top, what will happen? We have air filled within the two plates. You see the air close to the hotter plate get heated up and expand, which makes it less denser, get rise up. And then when it reaches to the colder plate on the top, it gets cooled down and become more denser. So we will have natural convection circulation for the left case. But how about our right case? If I hit the top plate, make it at a higher temperature than the bottom, where the motion of the fluid still happens. On this case, why? If for the the right part, you have the bottom at higher temperature, then you have the top at higher temperature than the bottom. The air get heated is less denser, so it keeps there at the top, right? And at the bottom, the temperature is lower, and the denser air remains at the bottom. It's stable. It's pure conduction problem because there is no bulk fluid motion inside. So although we have temperature difference, we have density gradient, how it changes due to temperature difference, and there must be the existence of gravity to result in the buoyancy due to the density difference. Then we can have the natural convection currents. And how there is a material property termed as the thermal expansion coefficient that's defined to capture how its density changes with the temperature gradient. Is by definition, the beta is defined as, here is the negative sign in the definition, the reciprocal of the density of the fluid, and how its density change with respect to temperature by holding our pressure at constant. Those density can also change with pressure. This is the definition for the volumetric thermal expansion. And let's begin with the most simple case for ideal gas. As you guys are taking thermodynamic courses, for ideal gas, we have the density, which is the reciprocal of its pressure, and we have ideal gas constant R over T. This gives us the density of ideal gas, and the T here must put as absolute temperature.
Just a question. So the main cause of the rotation of the fluid is it density or gravity? Say for example, if you do the same experiment in a vacuum tube, what would happen then?
There are three key factors. You must have gravity.
You must have.
Yeah, because there is temperature difference, and your density changes with temperature difference, right? At a higher temperature, it become less denser. At a lower temperature, become denser. Then it can start. Without gravity, it cannot flow.
So nothing would happen if there was no gravity and we heated that lower plate, for example.
Okay, so about gravity, no natural convection, right? Something interesting, among the first experiments in the space station, the Skylab, and afterwards, were done on materials processing. They were trying to make semiconductors. But when you make them on Earth, natural convection distributes the dopants in ways they don't like it. So they were trying to make semiconductors in space, so they would not have the natural convection.
Oh,
Yeah,
okay.
it's super interesting. Gravity, that's the name of the game, right? No gravity, that's why, do you know what a flame looks like in space? Have you ever heard? It's a sphere. Right. Like the fire goes up only when you have up. If there is no up, it's a sphere. Yeah, that's one of the dangerous things of fire on spacecraft. Right? Yeah. So natural convection is a phenomenon of gravity, right? And changes in density. If you have no changes in density, nothing happens. But you do happen.
Yes. Let's go back to the volumetric thermal expansion coefficient here. This guy is very similar like what we have, like K, the conductivity, alpha diffusivity. Beta tells us, and this only appears in natural convection, tells us how the density changes with temperature. And we say the air gets heated and become less denser. It applies to 99% of materials. But there are several exceptions. When you will become denser as heated up, we will go through it later. And for ideal gas, we have the density defined as the ratio of pressure over ideal gas constant and absolute temperature. Then just by the definition of the beta, we substitute what is the expression for ideal gas density. We have minus reciprocal of the density, and because it is holding pressure as constant, pressure and ideal gas constant can be taken out of the derivative. And then we have only the 1 over T left with respective to temperature. This guy gives us minus 1 over square root T. The 2 minus sign, negative sign, gives us positive sign. And this is 1 over T squared. And look at something here. We have pressure over density over ideal gas constant. What is that? Pressure over ideal gas constant. If you exchange the sequence of those guys over density, then you get temperature. So for ideal gas, only applies to ideal gas. Your beta volumetric thermal expansion coefficient is 1 over temperature. Must make sure you use absolute temperature for this expression. By now we have 2 places you must need use absolute temperature for radiation and for the calculation of beta. Because we can only have positive absolute temperature. So for ideal gas, your beta is always positive. The air at 1 atmosphere pressure at room temperature can be considered more or less as the same characteristic as ideal gas. But for liquid and other fluid, the book provides us in the appendix in table 8.6 the typical value of beta for water at different temperatures. When you go through those tables, you can see something here, this column. gives us the thermal expansion, but it's read as the beta times 10 to up to 6. So beta is typically small, and for liquid it's much smaller than what we have for gas, because gas is more sensitive, density sensitive to the temperature. And for liquid, I know some guys see very clear. Do we always have a positive value for liquid? For water, ice has more volume, so it has the negative, yes. So when beta is negative, it gives us that your density increase with increasing temperature, decrease with decreasing temperature. I searched online. Here is the water density of water as a function of temperature. Water, the density reaches the maximum at 4 degrees, and below 0, you can see its density increase. The slope is positive when temperature is smaller than 0, which gives us negative beta. And above 0, the density decrease with increasing temperature. That can explain why the ice is always floating on the surface of the lake. Let's consider the simplest case for laminar flow, free convection flow on an isothermal vertical plate. If I have a vertical plate like this, let's consider heating case first. And isothermal put at a higher temperature. Then the still air, we have Ts larger than T infinity. For this case, for this heating case, the air at the very, very beginning is steady, is still, is quiescent. It has no velocity. But when we have this higher temperature plate, what will happen? As we just saw these videos, we know the air will get heated up and then rise because it have less density, right? How would the thermal boundary layer develop for this heating case? We know, of course, it will rise up, right? Because it gets heated up. How would our boundary layer develop along this plate, vertical plate, start from bottom, and then what will happen? Keep growing. Yes. This gives us the thermal boundary layer, YCT. And for heating case, how about for cooling? We have the same configuration, but with a plate at lower temperature than the still air. By intuition, it tells us it will become denser and sink. Then how will the boundary layer develop? We know that it will flow. Like something like this. How would the boundary layer develop? From top or from the bottom? Top, yes. And then sink like this. This gives us the boundary layer development for cooling case. I pick the direction perpendicular to our plate as y direction. I would like to know how my temperature varies. At this point, which is on the plate, right? We see this is isothermal plate and the heating case. Your plate, the surface temperature is larger, right? Very far away from the plate, the air is get unaffected. Everything remains as the temperature of the air. It's very similar to what we have as in external flows. the temperature has an exponential, so look like the decay. And we can define the characteristic length here as our thermal boundary layer thickness. Then how about our velocity boundary layer? If we have the same axis, y, along the direction perpendicular to the plate, I would like to know how my velocity distributes along this direction. At the plate, what's the velocity of the fluid? 0, because of non-slip condition. Very far away from the plate, what's the velocity of our air? U infinity. But this is natural convection. We don't have any external force to impose the initial velocity. It is still air at the beginning. What happens is just get contact with a hotter plate or colder plate. So at the very far away, what's the velocity of our air? 0. 0 is increased at the beginning and then decrease to 0. And you will reach the maximum temperature at somewhere near the plate. We are super lucky because many years ago, people had already solved a bunch of differential equations to give us the exact solutions. The figure on the left gives us velocity profile. You see, there is a plot against some dimensional parameter, but it tells us at the surface of the plate, 0. Non-slip condition, very far away, 0, because it is still air. Just a portion of the air get affected by our hotter or colder plates. The figure on the right gives us temperature profile. Right? It's very similar like what we have in external flow. At the plate, for isotherm plate, it's constant. Then it decreases exponentially to that of the temperature of the air.